Greetings to all. Today we continue our discussions with primitive types. Categorize data types broadly into two. They are primitive types and objects. The primitive types are predefined data types. There are 6 of them. There are 6 numerical types and 2 other types. One is character, the other is used for Boolean true or false. Each of them have default value. All the numerical data types have 0 as a default value. Character is normally empty. It has the ASCII value 0. And Boolean by default is false. Each primitive type have their own memory size. Plus they also have a range, a minimum value and a maximum value. We already discussed that the default value for numerical types are 0. Now be careful when you choose your data type for declaring variables. Irrespective of the value assigned to these variables, for example, if I choose an int, doesn't matter whether I store a value 0 or 10,000 to it, still the memory allocated for that will be 32 bytes. And you can see on the screen the minimum and the maximum value assigned to them. Memory at runtime. Before we continue with primitive types, I would like to introduce to you my own visual model for representing memory allocated at runtime. The actual memory representations could be a bit different with more metadata, but I'm quite comfortable with this representation, so I hope you would also find this easy to understand, or else you could choose your own mental model. Basically, there will be 3 different memory locations every time a JVM instance is loaded into memory. And there will be a memory location for loading your bytecode and metadata. And there will be a stack and a heap. Now, in a 64-bit environment, for every instance of a Java application, the OS will allocate a maximum of, say, 4 GB. In the case of a 32-bit environment, it could be 2 GB. Out of this 4 GB, the OS normally takes 1 GB of memory for it to manage that particular instance of application, and the remaining 3 GB will be available to the application, which technically means the total data that your application use should not cross 3 GB. If your application requires more than 3 GB, then you probably need to make it into a separate application. You have 2 different instances of Java application running side by side in 2 different processes, and using RMI, remote method invocation, you can communicate between these 2 applications. Those things a little later in advanced concepts, but technically 3 GB could be the maximum memory that could be available for every single instance of Java, irrespective of how much RAM you have in your computer. At startup, the initial memory allocated to each JVM would be over 64 MB only. So you don't get 3 GB to start up with. When you start a Java application, you probably will have 64 MB of data. This may increase or in fact even decrease in size as the application runs. Java has something called as garbage collection, which keeps normally checking up with your memory and keep releasing unwanted memory. And if you find in spite of garbage collection, the memory allocated is insufficient for loading new objects, then what could normally happen is the size of your heap would increase, which means it will go back to your OS and say, hey, I need more memory, and hence the size of your application could increase. It is also possible to preset the size of an application before starting your JVM. Again, most of this I would be covering in the advanced concepts. The maximum size of each instance of JVM can be customized, and you can set it up, which means even though the OS can give you up to 3 GB, you would say, hey, for this Java application, I don't see why I need more than 1 GB. And you can tell your runtime, hey, don't go beyond 1 GB size. That is also possible. You can pre-configure the maximum size of heap that a JVM instance should occupy, and that too this maximum size can vary from application to application. So that is again a possibility. At startup, you can tell your Java host how much size maximum can be permitted, even though it may start with 64 MB, but you could specify that don't cross 1 GB if necessary. So yep, that is preconditions you can set before starting your Java application. In this diagram here, I have used 3 different memory locations. One is a working set. This is where information about your class, your application, the user who is trying to access it, security privileges, and the data type of each and every class or interface will be loaded. And also the bytecode will be loaded in the working set. Stack is where your local variables, that is variables declared within a method, static variables that are globally loaded, constants that we declare in our application, the current code that is being under the execution, the code under execution will be loaded in the call stack. This is assuming you're running in your single-threaded model, and for every new thread that you probably create, you will have another stack frame. So when a call to a method is made, it is loaded into the call stack, and after the method completes its task, the memory allocated for that method along with for the local variables will be reclaimed and made available to your application. We use the term depth of method call, which means how many nested method calls you could make from a method. So method A calls B, B calls C, C calls D, and so on. And the last method in the chain, once it completes, it goes back to the previous method and so on up to it reaches the first method. We call this as a depth of method call. Assuming that you have set a minimum stack usage size, and in that case, how many methods, nested methods call can we make at runtime? In a 64-bit environment, it is approximately 7,000. In my laptop, I checked and I noticed around 8,600 plus method calls was possible. So it varies, but it is safe to consider as you can make 7,000 nested method calls in a single stack. Coming down to heap. Heap is where JVM loads objects. Objects are loaded one on top of the other in continuous memory blocks in a heap. And once the heap, the initial size of a heap is 64 MB. So once the heap is full, then the garbage collector is called and asked to collect non-reachable orphan objects in the heap. And after the unwanted objects or non-reachable objects are removed, the available memory is reused for creating new objects, which means as far as possible, the JVM does not try to increase the size of the heap thanks to the garbage collection. It will try to manage loading objects within the available initial 64 MB. In spite of garbage collection collecting, if the available memory is insufficient for the new object, only then and only then another block of heap is being loaded or the size of the heap is increased. Some of the properties of primitive types. Few things, and these points are pretty important for us to understand while you write code using primitive types. Normally, when you declare a primitive type as a local variable, the primitive types, when the method is executed or method is called, these primitive types are loaded into the stack. But when you declare a variable as a global variable that is a member of a class, and when an object is instantiated for the class, then the primitive type that is a global member is loaded along with the object in the heap. By default, every single primitive type has a default value. You don't have to instantiate a primitive type. You cannot set it to null. And very important and interestingly is when I create an object instance and I try to assign that object instance to another reference, both the references share the same object. I create object A and I take the reference of object A and assign it to another reference. The first reference and the second reference both point to the same object. So any changes done to the value in an object will be the same for both the references. This is in case of objects. But coming down to primitive types, what happens is when you take a variable x, let's say we have stored a value 100 in it, and I take that variable x and assign it to a variable y, which is also of type int. Now, instead of sharing the data, instead of sharing the value, what happens in this case is a copy of that value that is in x is created and then it is stored in y. So what we end up having is two different memory locations with similar values, and changes done to x will not be reflected in y and vice versa is true. But when you go to an object, when you assign an object reference to another reference, they end up sharing the same object. So any modification done to the state of the object 1 through the reference 1, it will be reflected in reference 2. That's a very important point that we need to remember. So here is the demo of the code. I have two variables x and y. I've assigned a value 100 in x, and then I assign x to y. Look at the diagram that I've given on the right hand side. Instead of sharing the address of x with y, what happens in Java is, the second lower part of the diagram, you can see that the value 100 is copied and stored in y. So there are two different copies of 100. Any subsequent changes that you do to x, that is, I'm trying to change the value from 100 to 123, it does not reflect in y. So y continues to be 100 and x will change itself to 123, and you cannot set x or y to null. Instance variables. These are variables globally declared in a class which are not marked as static, which means for every object you create for a given class, each of them will have their own copy of instance variable. Let's take a case of a student. A student has a name, a student has an ID, a student has a date of birth, and student has an address. Now these four is unique for each student. It is not shared across multiple students. So when I create two or more instances of student object, I want each of them to have their own student ID. I want each of them to have their own name. I don't want them to share their address or their date of birth. So in that case, the variables that I would use to represent their ID, name, address, and date of birth, I would declare them as instance variables and not a static field. When you declare a variable as a static field, as in the second case where you see class variables, when you declare a field as a static field, what happens is it is shared across all the instances of a given class, all the objects of a given class. There will be only one variable loaded in memory, and that too it will be loaded in the stack, not along with the object in the heap. And this state of this static field will be shared across all the objects. So if you think there are some value for two or more classes to be shared, if it is the case, then you can declare it as a static field. For example, my company has a policy that it will only recruit people from India and will not recruit any employee outside India. Then my employee class will have a static field for country, if that is the case. Otherwise, don't declare a variable as static. If a value is shared across all instances of a given class, then declare it as a static field. Technically, it is not object oriented because it's not loaded with objects. Static fields need not be accessed through an object reference. So you just need to have a class reference to access its data. And most of the time you may not require a class variable at all. The reason why it's called as class variable is because you don't need an object reference to access it, whereas an object reference is necessary for the first item here, which is the instance variable. Then local variables, we already discussed enough about it in the previous session itself. A variable that is declared within a method is called as a local variable, including method parameters. The scope of these two are limited to the method as long as it is running, and these variables cannot be accessed outside the method. So let me quickly show you a demo of using primitive types. So here we have the example for local variables as well as global variables. I have prefixed a value g before the name of the variable to denote they are global variables. So in this case, gx and gy are both global variables, and they have been marked as static, which means I should be able to access these two variables without an object reference. And then I have two variables, data1 and data2. They're also global variables, but I have not used the static keyword there, which means you would need an object reference to access these two fields, data1 and data2. I also have a method. This method is not a static method, which means again an object reference is required to access this method called do some task. Inside the non-static method, I can access the static field. I repeat again, this gx is a static field, but I'm trying to access it from a non-static method. Possible, you can access a static field from a non-static method. Plus, you can also access data1, which is a non-static method, inside a non-static. Data1 is a non-static field which can be accessed inside a non-static method. Both are possible. But at the same time, if I had a static method, then static methods cannot access non-static field, which means data1 and data2, both of these cannot be accessed from a static method. Test it. I have a test class, and let's have a look at first working with static fields. This is a completely different class. Demo C is a class that contains a static field, and here is this class, another class, wherein the only way I can access the non-static field is by creating an object. There are two lines of statement here. In line number 14, I am creating an object for demo C class, whereas in line number 12, I'm directly trying to access it, and it's giving me an error. Even if I try to access it using the class name, say demo C dot data, I would still get an error. This is because it's a non-static variable and you would need an object reference for it. So in line number 14, 15, 16, I first create an object, and using the reference A1, I access the variable data1 and data2, assign a value to it, and subsequently I print it. Perfectly fine. Whereas I'm able to print the value gx, being a static field, I can use it using a class name. So this is why it's called as a class variable, class name dot field name, and I print the data at the top. You can modify the data if you want to, and you can call it and pass it on to any other method. Now the point here is a static field, once called, it is loaded into memory. It continues to be in memory forever. Whereas a local variable or an global member of an object, if the object is garbage collected, it's no longer in memory. A local variable is also, after the method execution is over, it's no longer in memory. But in the case of constant and static, once they are loaded into stack, they continue to be there for a very, very long time. And they are shared across all future instances. The last modified value will be there in the static field. For example, the initial value of gx would be 6776556, but subsequently I'm modifying it to 200, and then I'm calling another method called m1. As a result, what happens is the initial value inside M1 is no longer 6776565, it is 200 because the last modified value of that will be 200, and then subsequently I'm changing it to 50,000, and after that the method is over. It's no longer that. So method M1 is completed, and then I go back to another method, and that if I try to print the value of gx being a global static field, what happens? It continues to be in memory, and the last modified value 50,000 is printed here. Notice I change the value of the static field here, and then in another method I try to call it, and it prints the last modified value. So this way it keeps on changing, and this modified data will be shared across various other method calls. So let me try to run this code from public static void main, the portable executable entry point. I'm calling it here. Let me test it now. So what we need to do is run as Java application. You saw an option called run as server. If this is a JSP application or a web application, you probably need to host it on a server and run it. So that's when you use a run as server option. Here I'm just running as a standalone application, a console application. I have created an object, and then so let me have a look at it. I created an object A1. Initially the value of data 1 and data 2 would have been 0, and then I assign a value 1 2 3 4 and 6 7 8 9, and then subsequently I can see the modified data. If I create one more instance A2, and that it could have its own copy of data 1 and data 2, and their respective values will be different. You can experiment it when you try it out later by creating demo c space A2 equal to new demo c, and try to assign a different value for data 1 and data 2 and compare it with compare A1 and A2. You would see they would have two different sets of value. Whereas static fields are shared across all objects. So you can notice the initial value of gx was 67676565, and then I changed it at one place as 200 and go to another place and try to check the value. The last modified value 200 is available. Then subsequently I modified it from 200 to 50,000, and now I see the last modified value 50,000 on my screen. Well, this is about variable types in Java to start with. We saw global variables, instance variables, static variables, local variables, and parameters.